All right, welcome to day 2 of the Gilbert Stork Lectureship Award Seminar Series given by Professor Ian Paterson from Cambridge University. One of the requirements that Gilbert put into his bequest was that the awardee not be given a, quote, crappy plaque. Okay? And so I went on a search for something that wasn't a crappy plaque, and I found this at Tiffany. So maybe some of you recognize the famous blue bag from Tiffany on your graduate student salaries. I'm sure you were giving each other Tiffany gifts. So Tiffany had this thing advertised that was called a pyramid, but it didn't look like a pyramid to me. It looked like the more appropriate tetrahedron. So I called them up and I said, does it have 4 sides or 5 sides? Does it have a square base or a triangular base? And she said, well, it has a triangular base. And I said, yes, it's a tetrahedron. Call it a tetrahedron, not a pyramid. You'll sell more of them to organic chemists. So this is the inaugural Gilbert Stork lecture, and I think that this will be the memento that we give to all succeeding Gilbert Stork lectures as well, so that this trinket will become recognized and coveted and will occupy places of honor in all of the recipients' homes or offices. So when I got this, and I just set it up here to avoid, I was wearing white gloves a little while ago, so you see me in a suit and a tie and wearing white gloves, you might think of another career for me, but I wanted not to put fingerprints on this, and it occurred to me that this looked an awful lot like the cover of the Dark Side of the Moon album by Pink Floyd. And as it turns out, the late Sid Barrett was a citizen of Cambridge, and so you can see that we have a little light show here. And in fact, it reminded me of being at a Pink Floyd concert in Camp Randall Stadium with 80,000 crazed Pink Floyd fans a number of years ago. So you can see this photograph that Libby took is of the award, and it has this inscription, and this will be the only one that says inaugural Gilbert Stork lecturer.
Just in case this will do.
There we go.
He's nice.
So this photograph you saw yesterday, this is Gilbert Stork, and this is Samuel McIlvaine, and Samuel McIlvaine, his PhD advisor. One of the things you might notice if you've read the brochure, you can do the math. Gilbert arrived in Madison in 1942 and earned his PhD in 1945. So a 3-year PhD, which is pretty impressive in any era. Oops, running too fast here. Okay, so I just wanted to list some of the awards that both Gilbert and Ian have accrued in their careers, and I'll point out that Gilbert Stork won the award in pure chemistry, which is the top ACS award given to a young chemist, and that was in 1957. I'll just march forward 40 years. He was given an honorary doctorate from the University of Wisconsin. Some of the other notable things I'll point out is at age 39, Gilbert was elected into the National Academy of Sciences. That's a very young age to be inducted into the National Academy. You can see that For almost 50 years, he has been collecting the top prizes in the world associated with chemistry. You can see that he got the award in chemical sciences from the National Academy. He has won many honorary doctorates. You can see that he's a recipient of the Roger Adams Award, the Wolf Prize, which is often considered to be the predecessor to a Nobel Prize award. And he won the Derek Barton Medal recently from the Royal Society and the C. Brown Award, another ACS award. So, along an illustrious career, and as I said yesterday, we are the very happy beneficiaries of Gilbert's generosity endowing this lectureship that we'll have every year. So, Ian Paterson similarly has won many awards, and I should point out that he has just recently won the Royal Society's Natural Products Chemistry Award, the Tilden Prize. He is a Fellow of the Royal Society of Edinburgh, a Fellow of the Royal Society, FRS is what it's commonly called, and a variety of other awards from academics and industry. Interestingly, he has trained over 80 PhD students and postdoctoral co-workers, has over 250 scientific publications, and you can see that he has given more than 400 lectures around the world describing his research. So with that, I want to introduce Ian again, and he's going to tell us about a fascinating story on structure determination and synthesis of the Spirastrellolides. Ian?
Okay, thank you very much, Steve, and good afternoon, everyone. So hello again to those of you who were in my lecture yesterday, and those of you who've got better things to do and didn't come to my second lecture, well, I don't blame you. Anyway, so let me move on and introduce my second topic. Doing so, switch over. Find my talk. Right. Okay, so today will be a little bit different. My introduction in terms of, let's say, saying very nice things about Gilbert, I could easily repeat that, but I'll just really sort of summarize it in one slide. That Gilbert, back at Columbia, early this year, obviously very much enjoying chemistry, enjoying meeting up with visitors, and also, importantly, looking back not only on his amazing achievements in science, but his training of organic chemists over the years. So this particular t-shirt is actually the front of the t-shirt, which is a memento of the Stork Symposium back at Columbia when Gilbert turned, I guess, about 70 back in 1992. So this is the lineup of speakers. I guess there's about 8 of them, and really these are sort of famous names of people who worked with Gilbert, either doing a PhD or postdocs. But in the background, there are more than 300 names, probably about 320, of, again, students and postdocs that worked with Gilbert. And as I mentioned yesterday, approximately a third of those, which is well over 100, have gone into academic jobs. And if you extrapolate from that, what that means is over 100 people worked with Gilbert, a large number of people would have worked with those 100 people, so you would have propagation, and really a very large number of people are in the Stork family, if not the Stork group. So this is just an incredible contribution to science and the science of organic synthesis. Okay, so I'm going to move on, and what I kind of want to share with you this afternoon is, first of all, I want to get you nice and relaxed. So we're going to go to a Caribbean island, Tobago. This is one of the nicest beaches I've ever been on. So this is Pigeon Point, Tobago. And so this wasn't necessarily just a vacation, but I tried to get as close as possible to the location of the source of this class of natural products, which I'm going to describe the synthesis of, which is coral reef, not too far away from this point, probably about 50 miles out in this direction. Now, in terms of the source of the Spirastrellolides, I have to introduce this particular sponge. So this sponge is sort of bright red in colour, and in terms of size, well, it's not really, let's say, such a big sponge. It's actually reasonably common and it's Caribbean wide. It does have some predators, so it's not just natural product chemists looking to identify some interesting structures which may have some useful biological activity, but these turtles, hawk-billed turtles, essentially like to munch their way through many things, and one of those many things is this particular sponge here. So if you read this, so one of the samples of Spirastrella coccinea in Bahia contained a volume of this sponge that suggested the entire specimen was consumed at once. So these things are hungry, and this is part of the prey. Okay, so what can you find in Spirastrella coccinea? A range of natural products, but one particular class which I think is really quite unique, and in terms of, let's say, a synthetic chemist, one that really one would consider a beautiful structure. And so these things appeared in the literature, first of all, back in 2003, isolated by Ray Anderson and his group at UBC in Canada. And the initial structure, which appeared in JACS, is here on the right-hand side. And so what we have is sort of a macrocyclic lactone, spiracetal, tetrahydropyran, acid side chain with a couple of double bonds here, and lots of wiggly lines. So an interesting structure, but a real problem of stereochemical elucidation. So if you're going to start the synthesis, what on earth should you begin to make? Anyway, we started the synthesis probably soon after this paper came out, and thought, well, maybe we sort of work on the bottom bit, and progressively, maybe the rest of the structure would be revealed as Ray Anderson maybe isolated more material and could do more NMR work, and maybe could actually get a crystalline derivative and obtain an X-ray sample, X-ray crystal structure. Okay, so in terms of activity, it's pretty potent. It's, I guess, low nanomolar activity as antimitotic agent. It's really very scarce, and so isolating more than a few milligrams is tough. In terms of methods of action, it's quite different from the compounds I talked about yesterday. Spirastrellolides are protein phosphatase inhibitors, and particularly are active against protein phosphatase 2A. So there's some similarity with some other natural products like colliculins and oxidaic acids. So this compound, of course, attracted our attention, and not surprisingly, many other synthetic groups said, wow, this would be a really nice project to work on for various reasons. First of all, there's uncertainty over the structure. Secondly, it's very biologically active. And thirdly, we even get some funding. Probably it's in that reverse order. So, other synthetic contributions in the stage, Jeff Brabander, Craig Forsyth, Richard Sung, here in UW-Madison, Amy Smith, Andy Phillips, and someone who I sort of compete with from time to time, but he certainly has a lot more funding than me, is Alice Ferschner in Germany. So this structure got our attention, and we started to think about, well, how can we put it together, and how can we determine the stereochemistry as the synthesis progresses. But after about a year, so 2003 to 2004, there's another paper that came out from Anderson's group, which provided more information on the biological activity, but also reassigned the structure. And so the revised structure is really quite different. So in the top part of the molecule, this DE spiroacetal actually becomes a bis spiroacetal, so a DEF ring system. There's this thing gets, hydroxyl group here gets replaced by chlorine, and essentially then we still have the same side chain. But because they managed to isolate more material and did a lot more NMR experiments, progressively they could assign some of the stereochemistry. So some of these wiggly lines now have been replaced by relative stereochemistry, but within this structure there is actually still something like 16 possible stereochemical permutations. Because from the NMR analysis, one could assign stereochemistry in blocks, like this block here, this block here, this block here, maybe this block here. But relating those stereoclusters together is actually quite challenging. So the Spirastrellolide A is the free acid, but what was actually isolated and purified, and in terms of activity, it's pretty much the same as the free acid, is the methyl ester. So it's converted to the methyl ester and isolated. Okay, so if you look more carefully then, so these color-coded regions, so the blue region, the stereochemistry is assigned, the green region, the stereochemistry is assigned red, and this sort of pinkish color on the side chain. But altogether then, what we have is a situation where there's still 16 possible stereoisomers to consider for synthesis. So in the top piece, this sort of bis spiroacetal, really very unusual structure, benefiting of course from stabilization from the anomeric effect, and also having this chlorination here at C28. And all the substituents are equatorial. With the bottom spiroacetal, which is unsaturated BC, again, if you look at it, this benefits from stabilization from the double anomeric effect. So in terms of synthesis, this is going to help. And again, all the substituents are equatorial. So the relative stereochemistry, as I say, between those four highlighted regions was initially unassigned. So what do we do in terms of considering a synthesis? Well, ultimately, we want to go after the whole molecule, but progressively, maybe we could try and make some fragments, see if the NMR data for those fragments agree with that for the natural products. And if we put, let's say, stereoclusters together, maybe one combination relative to another one or other possibilities matches the NMR data better. So progressively then one might build up a much better picture of what the structure of Spirastrellolide A actually is. Okay, so this is very much early days. So this would be certainly 10 years ago, our initial synthetic planning. So here's the structure, and okay, macrocyclic 38-member lactones. We close this at some stage. We would build in this side chain, this undefined stereocenter, and obviously one could make either an enantiomer selectively, and we build this in by some kind of Stille-type cross-coupling. The bottom piece, what we didn't know initially, was the relationship of this stereocluster here, including the spiroacetal, relative to this cis disubstituted tetrahydropyran and A-ring. So maybe we should go after the two possible permutations and see if one has a closer match to the NMR data. Bearing in mind, of course, is what you'll be doing is you'll be comparing something which is half the structure with something which in the natural product is conformationally much more organized through having the macrocyclic skeleton. So, who knows what would come in terms of doing that comparison. And so for the top piece, which is going to become the DEF ring, we thought we'd go after something like this tetracyclic lactone, and maybe this shows you our level of synthetic planning. We would say it's C25, C26, carbon-carbon bond formation. So it doesn't really reveal too much about how we're actually going to do it, but somehow we have to think of a way of connecting the bottom piece with the top piece. Okay, so let's maybe look at this and unravel it a little bit further. So we want to get the two possible permutations of the A-ring stereochemistry relative to all of the stereochemistry in the rest of that region. So if you unravel the BC ring and sort of stretch it out and think, well, probably we have to put some protecting groups on, although we don't like protecting groups, but they are necessary, certainly necessary to assemble something like this. And what we saw is, okay, certain relationships of stereocenter, certain patterns, which might help us in terms of thinking how we could sort of build in the appropriate carbon-oxygen skeleton at the same time as controlling the necessary stereochemistry. And so this Z-alkene would come from an alkyne type addition into carbonyl and a linear reduction. So kind of stretch it out and unravel it. So break that bond, we've got alkyne, this 1,3 antidiol acetonide, and maybe if we cleave that, we'd get back to an A-ring with only two stereocenters, and we could control this center from that center using chemistry which I described yesterday. This part of the molecule, we have 1, 2, 3, 4, 5 contiguous stereocenters. 4 of those stereocenters have oxygen. One could think about starting with a carbohydrate, but we don't really do that kind of construction. It's not to say that it wouldn't be a good way of doing it. So we thought probably we could start with something like this, which of course would come from tartrate. Okay, so that's enough in terms of basic retrosynthetic analysis. Let's kick off the synthetic effort. So kicking off the synthetic effort, well, it's not too many steps to get hold of this, and get hold of this on scale. So slightly modified Brown annihilation. So instead of using the usual IPC, this is another monotherapy from Carey, which actually gives you much higher enantiomeric success in the product. So do the annihilation, treatment with base, oxymical sets the cis tetrahydropyran ring with high selectivity. And then we could kind of go in two directions, taking advantage of the pseudo-symmetry of that cis disubstitute tetrahydropyran, and do some manipulation on one side and some manipulation on the other side. So in this direction here, we cleave the double bond, we do another asymmetric annihilation, sets that stereocenter with this configuration, and then a few fairly straightforward steps then gets you through to this C1 to C aldehyde, C1 to C11 aldehyde with 3 defined stereocenters. And what we want to do is to get the other permutation where essentially that stereocenter stays the same, but we invert these two relative to that one. So you can go from this common intermediate, really sort of 4 steps, so that you kind of switch it over essentially. So this C1 becomes C1 here, and this becomes this aldehyde. Do now the allylation, silent protection, ozonolysis. That gets you through to here, and now if you mentally turn that over, it gets you to that. So without too much effort, we could make these two initial C1 to C11 subunits. Now we can set the C11 stereocenter by using this chiral ketone. And this particular chiral ketone, if you just rely on, say, the cyclohexyl boron enolate will give you, maybe in such a situation, about 10-to-1 selectivity, which is reasonable, but one can reinforce that selectivity with a chiral ligand. So here we actually use the IPC boron chloride. That gives you pretty much exclusively the 1,4-syn adduct. Take advantage of this stereocenter and Evans Cena reduction to do anti-reduction to give this diol, and then a few steps which involves tying up the acetonide, knocking off this benzyl group, going to the aldehyde, chain extending to give the corresponding tauron alkyne. So we made this, and we started out with this one as well. So this is now bis epi relative to this one, and made this. With the aldehyde component for the alkyne addition, we started out from tartrate, so making this aldehyde acetonide. Again, asymmetric alylation, methylation. So this is now, as I say, back in probably about 2004. 2 steps gets you through to this. Using some chemistry which I described in the context of our synthesis of leodermatolide, this lactate-derived ethyl ketone, make the boron enolate. You actually have a very highly selective anti-aldol addition, and that controls the stereocenters of C23 and C24. So a little bit more manipulation, which includes cleavage of this, gets you through to here, hydrabrate oxidize, oxidize again, gets you through to the aldehyde. So I've made another fragment. While making fragments, start to join them together. And so joining them together, so lithiating, adding into this aldehyde, oxidizing, Lindlar gets you through to this enol. Now I mentioned yesterday that at the end of the synthesis, particularly of your reasonably complex polyketide, you have to get the protecting groups off. But in this case, you also have to get the protecting groups off at an initial stage and sort of figure out what we're making. And what we tried to do was take off protecting groups in a sort of stepwise manner, but that didn't really work that well. So we actually stripped off all the protecting groups with HF acetonitrile, so knocked off the TBSs and the 2 acetonides, and this TBS as well. So this one all cyclized up to give this C1 to C25, and when we did it with the other alkyne fragment here, which was epimeric here, epimeric there, then it gives you this. So these two, of course, by just initially looking at the NMR spectra, are very, very similar. If you look at them carefully and compare particularly the proton spectra relative to that region of the natural product, you begin to, well, start to gamble. One of them maybe fits a little bit better than the other. So here are the 2 possibilities again. And what we found, so this is the comparison now with a particular region of spirastrellolide, and expanding this region C7 through to C9 here as well. If we were going to put money on it, in other words, or maybe just toss a coin, we convinced ourselves that in terms of the better match, that the one which looked better was this subunit 1 here. So therefore we kind of put all our effort into sort of progressing the synthesis based on this particular stereochemistry. So I emphasize that that gives you maybe a hint of what the relative configuration is, but we don't have a clue of what the absolute configuration is at this particular time. What we considered doing to try and figure out what the absolute configuration was is maybe we could do some kind of collaboration with Ray Anderson. And what we proposed to Ray was the following. While we've kind of made, or we can make these sort of fragments in sort of southern hemisphere, or we could probably even go after something in the northern hemisphere, and maybe sort of simplify that back to a structure like this. So the question was, did he have enough Spirastrellolide A to be able to do some degradation? So at the time, he'd actually managed to degrade a lot of Spirastrellolide A by simply trying to make various derivatives to get something hopefully crystalline for X-ray. But he did have a little bit left. So he agreed that he would take his sample of Spirastrellolide A or methyl ester and send it on paper what we think about this fissional diol, these are kind of oxidative cleavage. And if that happened, then some kind of reductive workup should give a fragment which looks a bit like this. So if we therefore, by synthesis, go after this with either these two up or these two down, maybe we can actually correlate the degradation fragment, and that would give us a much better idea of what the stereochemistry is of the bottom part of the molecule. Okay, so on the synthesis side, all we had to do was sort of step back a bit, and instead of having all of this stuff hanging off here, we just need to truncate it a little bit. So again, unravel this BC spiroacetal, same idea, alkyne into the aldehyde, appreciating here now sort of a syn relationship between this oxygen, and so that would arrive then at this alkyne, now the simpler aldehyde, which only got 2 stereocenters. So we now really wanted to have perhaps a better synthesis of this piece. And what we started out with then was not to do the brown alylation, but instead, and this is really very scalable chemistry, use Eric Jacobson's excellent hydrolytic kinetic resolution method to get this epoxide building block on large scale, Grignard opening, cross metathesis to this enoate, and now with the stereocenter set, do as we did before, oxy-Michael, reduce, oxidize. And now because we felt from that initial NMR comparison that the more probable relative stereochemistry of the bottom piece was as shown here, then we don't actually have to do an asymmetric alylation. We can take advantage of substrate control. So now under chelation control with titanium and allylsilane, and in the allyl group, sialate cleave gets us through to this in reasonable selectivity. So again, repeat our chiral boron enolate addition, and goes through to this point here. And again, this reduction, so quite similar, building up the alkyne through the dibromoalkene, gets us through to this. So in comparison with the, let's say, the first generation approach to that fragment, this is much more scalable, so you can make certainly multi-gram quantities of this without huge effort. Okay, so now if we take this, and we take this simpler aldehyde piece and do really the same chemistry again, going through this enone, now we want to remove this PMB ether and this PMB ether, but keep the silane protecting groups on. Well, we can do that with DDQ. It nicely closes up to give this, and then finally we actually remove the silane protecting groups to get fragment A. So we made this, and we made the corresponding compound where these two hydrogens are down. And then we sent them to Ray Anderson and hoped that we'd get an answer back. But the answer back was, oh yeah, we tried to do this degradation, but we couldn't fish out anything sensible. Even having your authentic samples of these fragments so that we could sort of look for what we need, didn't actually manage to find the same compounds in the sort of degradation mixture. Okay, so we didn't really make any progress here, except we had a better synthesis of this fragment. Okay, so let's go back to the synthesis plan. So I've talked about this. What I haven't really talked about is how we're going to assemble this. So this is definitely the most challenging part of spirastrellolide for synthesis. So highly oxygenated, you have to put the chlorine in. You have to, of course, control the configuration of the acetyl carbons. And you have to have a sort of scalable synthesis, because realistically, one would need gram quantities to be able to go forward to try and connect fragments together. Okay, so our initial idea was some kind of, okay, mentally take that back to a carbonyl. Maybe we could do this by an HWE and then a hydroge. So that would give you kind of something which corresponds to this piece, which is actually this bicyclic fragment with the methyl stereocenter. And the corresponding phosphonate bit would be this, which has got 3 contiguous stereocenters. So we need to make this, we need to make this, we have to sort of join them together and then hope maybe we can convert through to this. So the guy who worked on this, at least this particular fragment, was Olivier Boisseleau, and his full-time job is at Syngenta, and he managed to persuade Syngenta to come and work in my lab for a year. I thought that was great. But they had a very good reason for doing it other than he enjoyed chemistry, is that Olivier previously worked with Novartis in Basel on the discodermalide project. And one of my students was on the discodermalide project funded by Novartis, so she spent some time in Basel. The two of them got together. So I think Olivier's main reason for coming back to my group is so he could spend a lot more time with his girlfriend. Actually now is his wife, so it's kind of a very happy ending. Anyway, that's a digression. Okay. So Olivier obviously quite liked doing cross-metathesis. We can do this. It's not great, particularly because you get a mixture of double bond isomers, so around about 4:1. We can sort that out in the next step. So if you do a Sharpless asymmetric dihydroxylation, importantly you actually get good EE. And with the Z isomer, of course, you produce a diastereomer. And so chromatographically you can separate the major diastereomer, which is the one here, from the unwanted minor one. So we'll take this through to the corresponding aldehyde here, do some Brown proselection. So sets those two stereocenters, and then actually quite tricky chemistry here. What we do is knock off, well actually we oxidize this to the ketone first. That particular stereocenter, of course, looks quite delicate because the double bond can move with the conjugation, so one has to be careful here. So oxidize the ketone, knock off the TES. That then closes onto the ketone, in the presence of methanol you form the mixed acetal, and then finally you cleave the double bond to the aldehyde. So you get through to this, and you can preserve that stereocenter. Okay, another piece to make. So we start with this really very simple aldehyde, take advantage of this Brown procedure, which was developed subsequently by Ohlschlager. Where instead of having a methyl group here, you have a chlorine. This actually works really quite nicely. It's chloroalylation set at required relative and absolute configuration here with good selectivity. So methylate, and now we have this allylic chloride, and we can do a dihydroxylation again. Now if you do dihydroxylation without chiral ligand, just osmium tetroxide NMO, you get a useful level of substrate selectivity, about 4:1, 5:1 in the anti-sense. What you would expect if you had, let's say, a hydroxyl or an alkoxy group there, you get the same consequence having chlorine there. But if you do it with a chiral ligand system, so a Sharpless, you actually get very good selectivity. So a few steps through to this aldehyde, elaborate through to this phosphonate, and now this barium hydroxide procedure, which I described yesterday, gives the corresponding enol in this striker type reduction. So in my lab, when I was enjoying and of course working very hard as a postdoc with Gilbert, there were various key people, Eiichi Nakamura, who I mentioned yesterday, who currently is in Cambridge giving a lecture while I'm here, and Jeff Stryker, who is now at Alberta, Canada. So Jeff's chemistry in a way that caused us to look at this sort of copper hydride procedure, a very clean way of reducing enones to the saturated ketone. Okay, so maybe this would be a suitable precursor now to give the top piece, so this bis-spiracetal, the sort of DF ring system, the appropriate oxygenation, and of course including the chlorine. Well, the initial results were very frustrating. So if you treat this thing with acid to try and knock off the acetonide, hydrolyze this and hope it zips up, all you manage to do is to destroy some stereocenters. So you go from this through to the corresponding furans. So this is really bad news. If we play very hard and sort of screen various conditions, eventually after some considerable effort we came up with Dweck's acidic conditions, 70 degrees centigrade for a certain optimum period of time, can't remember exactly how long, and on a good day, and importantly on a small scale, we got 40% yield of this system here. And the NMR analysis of this, so things like NOEs and the proton chemical shift comparison to spirastrellolide, gave us confidence that yes, this does actually correspond to that appropriate region of spirastrellolide, but again, we don't know the absolute configuration. So we could make this, and we probably made a few milligrams, but this was really a serious early stage bottleneck. Because as we tried to scale it up, the yield went down. So we had a real problem. How are we going to make this particular fragment or something close to that fragment on a useful scale, i.e. sort of gram type quantities? Okay, so now there was very important development. So this is 2007, so we're about maybe 3 years into the project. We sort of found out a few things which we can do quite well. We found things which we can't do that well. We found things which we can't do at all. And so another congener of the spirastrellolide, something called spirastrellolide B, lacking the double bond in the BC ring system, was isolated by Ray Anderson. And again, they could make various derivatives of this, and one of them that we made was to tie up this 1,2-dialysate-acetonide, tie up this 1,2-dialysate-acetonide. Also another difference is there's no chlorine here relative to spirastrellolide A. Now they could do a little bit of degradation, so kind of an oxidative cleavage of the side chain and converting C4 into this parabromo phenacyl ester. This time, and it did some damage to this part of the molecule, so this acetonide dropped off and you got oxidation of the ketone. But this pretty much still looks like spirastrellolide and it's crystalline, and so they got a crystal structure. And the good news was that all of this relative and absolute configuration corresponded to what they had in that second paper in Organic Letters, and also corresponded to what we'd deduced in terms of our sort of building up some permutations of stereochemistry of the bottom part, that the relationship of that tetrahydropyrite through to those stereocenters corresponded to what we called subunit 1. But the really good news was that the absolute configuration corresponded to what series we were working in, so we didn't have to go back to the beginning and sort of swap everything else, swap everything for the enantiomeric starting material or enantiomeric chiral reagent. Okay, so 2007, I think maybe it's time for a commercial break. Whoop. Here we are hunting again. So maybe we're back at the design stage, and back at the design stage, at least in my group, usually involves a trip to the pub, usually on a Friday evening, and usually with a pad of paper and pen and sort of sketch out ideas, and we sort of revise our synthesis, have another beer, revise our synthesis, and eventually come up with what we think is our best possible route. So after that revision, we now have what's called strategy evolution. It does sound grand. What we wanted to do now was, we knew what stereochemistry we should be able to be building up. But what we didn't know is what's the best way of connecting the top piece with the bottom piece. So this is like undefined carbon-carbon bond formation. So if we unravel this, chop the side chain, stretch this out a bit, think where maybe this could come. So we knew that we could do this sort of BC spiracetalization, particularly if you had PMB ethers here, that worked quite nicely with DDQ, and we could probably keep all the other protected groups on, with the exception of this one. And we had various ideas how we could connect the bottom piece with the top piece, but our kind of best ideas, our main bets, were to go for two possible strategies. So some kind of Julia olefination followed by hydrogenation to make C25, C26, or alternatively, maybe this could be a double bond, C24, C25, and maybe then we could do some kind of, actually no, it's C23, C24, so if you can mentally imagine retrosynthetically dehydrating this to a double bond, so you have a double bond there, single bond there, maybe we do a Suzuki coupling here to make that bond, and then some kind of hydroboration to introduce those two stereocenters. So those were our main ideas. We didn't know which is going to be better, so we of course have to pursue both of them. So what we needed then was various fragments. So this sulfone to explore the Julia coupling strategy, and this vinyl iodide to have a look at the Suzuki hydroboration alternative. We had a good synthesis of this now, we could produce some multi-gram quantities, but a real sort of missing component was how on earth are we going to get this DEF bispiracetal and get it on scale. So almost certainly went to the pub again, had a few more beers, thought very hard. Well, we've been trying much too hard over building up this. Let's try and simplify it. So if we simplify it, so if you unravel this and notice that these oxygens are going to come in from a dihydroxylation, open up the acetal, maybe this bis ketone, bis alkene, we could do a double asymmetric dihydroxylation on it, touch it with a little bit of acid, and magically it would zip up to give us the required compound. So where this would come from is, okay, we have to make that carbon-carbon bond, so an aldehyde, ketone, some kind of either HWE or aldol, dehydration, etc. And what we found from our preliminary studies is, yes, if you have this allylic chloride, then sharpless works extremely well, 97.3 to give you this anti-relationship here. And what we found previously as well, so with this system, even though it's an EZ mixture, you get very high E for this. So if you used essentially the same ligand system, but do both double bonds, we could perhaps try and do a lot more useful chemistry in one pot. So to make this aldehyde, so deconjugated aldehyde, this lactone, lactate-derived enolate again, aldol addition, salylation, cleavage back to the aldehyde gives this. This is now changing the oxidation state of this, which was previously TBS ether. Now we're going to have it as a ketal, acetal. So they're using chloralylation reaction, methylation gives you this. This can be done on multi-gram scale. And now these can be united. So boron-aldol reaction, we actually made the mesylate and eliminated and did the Stryker reduction to get through to this. What we had to do at this point was reduce the ketone to the alcohol, knock off the TBS, and then importantly do a double oxidation by Swern so you don't get any cyclization to give this diketone. And now call on Professor Sharpless to work his magic, and maybe this could be converted into this. So of course, I wouldn't be presenting this, and I wouldn't have finished Spirastrellolide if this key reaction had not worked so well. So in fact, this thing, under reasonably standard AD conditions, what you fish out initially is this system here, so kind of a cyclic hemiacetal mixture there. So, NMR is not looking that great, but certainly we've introduced the oxygenation. And now we touch this with a little bit of mild acid, PPTS, methanol, the thing zips up to give us the DEF. The NMR analysis, again, sort of supports that we've got all the stereochemistry correct, and so we've made essentially all these bonds with the right configuration. You get some minor diastereomers, particularly relative to that stereocenter there. So after silylation of that mixture, the minor diastereomers can be separated out and re-equilibrated under acidic conditions. So you can sort of build up gram quantities of this key intermediate. So what had previously been a serious bottleneck now opens up completely, and we can get useful quantities of this key fragment. And then just selectively knocking off the test ether and oxidizing to the aldehyde. Okay, so now we have a route to this. We have to think of how do we make this, and explore carbon-carbon bond formation at C26. So let's have a look at the Julia coupling strategy first, which I think is the first one we explored. So this Seebeck-Frater alkylation of this system here gives you the anti-stereochemistry, sticks the methyl group in, bit of manipulation through to this aldehyde. Now that's sort of Evans glycolate aldol through to this. Allal-Grignard gives us deconjugated ketone. Take advantage of the PMB ether and the ketone and chelation, so zinc borohydride, methylation, knock off this, gives you this, bit of silylation, then bisylation, knock off this one, it is a bit steppy, make the sulfide, oxidize the sulfide through to the sulfone, and that is the appropriate sulfone to explore the Julia chemistry. So we can make this, but of course it is quite a few steps. I don't know how many there are, probably at least 12 or 13 steps. Trying to do the carbon-carbon bond forming reaction under sort of Julia, modified Julia conditions was really very disappointing. The best we could get, and probably again on a small scale, is about 30% yield, because the problem here is this aldehyde is really very hindered. It's got all of this bispiracetal nearby, and also it's rather delicate, so you don't recover any unreacted starting material. You either get the desired compound in sort of 30% yield, and everything else is junk. So this is like, again, a bottleneck. So, but even though we got some material forward, what we could do with it is, okay, selective hydroboration here, and then a reduction of this internal double bond, and then desmar to the aldehyde. So this was actually what we wanted to make. Now, but with, let's say, limited resources, one realizes that it's going to be tough to bring material through if you've got 30% yield right in the middle. So we didn't really like that at all. So what was the alternative? The alternative is to explore the Suzuki coupling. And so to make the vinyl iodide, firstly, is much quicker. It's only about seven or 8 steps. So this is actually a known compound, this iodoenal, glycolate aldol, Allal-Grignard onto the 1-ribamide, give it deconjugated. So it's a bit similar to what we did previously. Zinc borohydride, methylation, knock off the test ether, and gives this. So it's now only 3 stereocenters, double bond, vinyl iodide. Now we take the aldehyde, Wittig methylation. Now in one pot, hydrabrate with 9-BBN to get the borane, combine it with the vinyl iodide in appropriate plating catalysis conditions, which what turned out to be really useful as this set of conditions here. And now the yield was more than double. In fact, realistically, it was probably about 3 times the yield relative to the alternative Julia coupling. So we could build in the trisubstitute double bond, we could make that carbon-carbon bond. Now we've really got into unknown territory, because if this was the other way around, so if the methyl group was on here, and if you had this allylic stereocenter, there's a lot of information in the literature, a lot of precedent for what phase selectivity that double bond should undergo in hydroboration. But for this kind of system where you want to hydrobrate this way around, certainly is much less known. So therefore we made various model fragments and explored those, and really didn't get a clear answer. Some of them gave selectivity in one direction, some selectivity in the other direction, and in many cases there was really sort of just modest selectivity. But in practice, in this system here, in the sort of early stages, we've got this so much better now that we do indeed get hydroboration from the correct face, and what one can do then is a double hydroboration. So this double bond goes first, and then secondly this one goes, and then you, probably to show there, then we silylate to get now the tris test ether here. And this correlated with material which came through from the Julia coupling product, and therefore that allowed us to assign the stereochemistry at these 2 centers here. So we knew what those 2 centers were. Okay, so moving forward, the Suzuki coupling sort of wins the competition in terms of how we're going to connect the bottom piece to the top piece. We have this fragment, we have this fragment, we have this. Maybe we start to put things together. Okay, so putting things together, that primary test ether we can knock off with mild acidic conditions, oxidize to the aldehyde. We have this alkyne, so lithiate, add it into the aldehyde, linear hydrogen oxidized through to here. PMB, PMB, PMB. DDQ, the whole thing should zip up to give the BC spiracetal, as shown there. And that does indeed. So you form the BC spiracetal, but unexpectedly, we lost the test ether. This one here came off cleanly, and so the student who did this, Steve Dalby, he was really keen to stick that test ether back on. But I persuaded him and said, well, ultimately you've got to get the protecting group off, so why not take advantage of it dropping off, as you've achieved more than one thing in that transformation. Maybe the system is also telling us something that it doesn't want to have a protecting group there. So let's go forward with free alcohol. So we could get this, and now this is C1 through to C40, so it's looking a bit more like spirastrellolide. And very importantly, of course, it's not just a case of building up fragments, connecting them together, but if you're going after something like one of these large ring macrocycles, you have to be able to cyclize. And this was almost unbelievable, because our first attempt at macrolactonization, so when you get through to the right oxidation state, this acid alcohol, this I think was our first attempt, probably a few milligrams, room temperature, not doing anything special. This thing cyclized amazingly to give now this, which really had a very nice NMR spectrum. So we could make the 38-membered macrolide core. However, we had to think about how to build in the side chain. And what we would like to have done was selectively remove that TBS ether and grow the side chain here, and then eventually remove other protecting groups. We couldn't do that. We could not, so it seems like a very simple transformation, to select it, we remove that TBS ether, because that TBS ether is actually in quite a crowded position, probably to some extent it's sort of buried into this macrocycle or held over it. So all we could do was really just knock off all the protecting groups. In doing so, probably for one of the first intermediates in the synthesis, we got something which was highly crystalline, and we got an X-ray. And so this is a crystal structure now, which we're obtaining here. And it tells us, well, several things. Firstly, all of the stereochemistry which we thought we put in turns out to be correct, so it's always nice to have that confirmation. And it also has this fairly, well, in fact, highly organized internal hydrogen bond network connecting up the hydroxyl groups with the ether oxygens, as sort of suggested by those dashed arrows. Okay, so back to planning. What we need to do is, we have to build in this whole side chain. We've made the microcyclic acetone. We have to complete the synthesis by building all of this. So at least this looks like a relatively simple fragment. And one can get hold of it, either an enantiomer from malic acid or the dimethyl ester through the dibromo alkene, and then this sort of selective process here, where what we do is, first of all, we take out this bromine reductively, and then we replace that bromine with tin to get the Z-vinyl staining, where then we knocked off this thing and made the methyl ester, so you can make the enantiomer as well. And then we practice the chemistry, so with our top piece, which we had reasonable quantities of, we could go through to this allylic carbonate and do a parallel Stille coupling with this, and through this intermediate we actually build in the whole side chain. And of course, one doesn't have to use this, one can use this because it should give the same intermediate, so either way, and this will actually work out a little bit better to give this. So we can build in the side chain on the top of the molecule without the whole macrocycle. Question is, can we extend that and get it to work when we've got the macrocycle there? This actually turned out to be quite hard. Firstly, it's okay, we could knock off all those solid protecting groups. So what we have, first of all, is a pentahol. And what we'd like to be able to do, but couldn't do it, would be a selective oxidation of the primary alcohol to the aldehyde, just to leave all those hydroxyls unprotected. We could not do that. We always got oxidation at other positions. So we had to put some groups back on. So tie up 1,3-diol as acetonide, 1,2-diol as acetonide, and then we've got some mixed acetalate there where we can knock that back to the alcohol. Then oxidize here to the aldehyde, because these things are now protected, and then do the Wittig methylation to give you this. To do this cross metathesis, we really had to push it very hard. So 80 degrees benzene, and leave it for a reasonable amount of time to try and get a useful level of conversion. Never really went all the way. So what it was telling us again was really that alkene is now very hindered because it's next door not just to the DF bispiracetal, but probably is held over the macrocycle, and one really has to push it very hard to make any of this alkene product. So we can now take this and do the parallel Stille cross coupling, and we did it with separately in two experiments with this enantiomer, the R configuration and the S configuration. And the two products, even though that stereocenter, when you draw it this way, looks as if considerable way from that macrocycle, those two diastereomers by NMR are very different because, of course, that side chain is held over the macrocycle, so it's in a chiral environment which is in close proximity in terms of sort of 3D. Now we could actually look at some of the NMR data of Ray Anderson and found that this configuration corresponds to the bisacetonide which he'd made from Spirastrellolides. Therefore, that was really good news. We'd essentially cracked the first synthesis of spirastrellolide. And all we had to do was remove, now we only had to remove a couple of acetonides, and so we could do that PP2S methanol, gave us now our first sample of synthetic spirastrellolide amethyl ester. But even at this time, slightly worryingly, when we made our first sample and ran the NMR spectrum, particularly the proton spectrum, there were really some differences relative to the published data. Of course, that's worrying. And when we ran it under maybe somewhat different conditions, the NMR changed a little bit as well. So to totally tie down with confidence that we had synthesized spirastrellolide amethyl ester, we need to get an authentic sample. So fortunately, Ray Anderson sent us an authentic sample. We ran the NMR. The NMR was then a bit different from the published NMR. And what we had to do finally was to purify by HPLC the authentic sample, our sample, and run the NMR under identical conditions, and then they completely matched. So what that tells you is, even though we were at what we thought was the end of the synthesis, maybe subtly something strange was going on, and we didn't actually have the structure that we thought we had. Anyway, so this is good news. Not only did we go to the pub for some beers, but of course we had a really nice party in the department. And so that was sort of now way back 2008, I think we finished that synthesis, and now we had to put out a couple of full papers 2 years ago in OBC and various reviews. But maybe time to pause to think. Firstly, there's a whole family of spirastrellolides. Maybe we could use this particular route to give not just spirastrellolide A, but this is sort of probably make some other things. And maybe we could use this advanced intermediate, this sort of pentanol macrocycle, and certainly on paper we thought we'd be able to get all the ones in red. We of course could go forward and make analogues. But that was actually a lot of work. And right about that time, this may sound familiar to people, but all the people on the project wrote up their thesis or finished their postdoc and left. And I had one new student starting, and he was actually a very good student, and he was a very good student because he'd done a project in my group already. But he wasn't quite sure that he wanted to do a PhD. So he left me and joined a management consultancy company in England. And after about 3 months, he contacted me saying, I can't stand this, it's so boring, and I want to come back and do a PhD. Fortunately, I managed to get funding for him, so after a delay of really about a year, he came back and started the PhD. And we thought, well, why don't we try and make spirastrellolide in hopefully a more efficient manner. So, commercial. This is actually a very nice pub. So those of you who've been to Cambridge, so Steve, I don't know if you're ever paying for a drink at the Anchor. There's a kind of nice pub there on the river. Okay, so we've had initial strategy evolution. This is strategy evolution 2 for hopefully second generation synthesis. Because we knew various things. First of all of the stereochemistry was reliably defined. So we didn't have to go through this process of trying to make some fragments, do comparisons, trying to figure out what's correct. And then whatever fragments we got, how do we connect them together? How do we actually get through to the end? So we can now be a lot more focused in our planning. And what would be nice is, okay, cleave this open, unravel, and so really pretty much in the penultimate step, we would do a macrolactonization, we have some kind of protector group there and just knock it off to get either methyl ester or the free acid. So if you take this now, what we're doing is we're kind of inverting some of the order of steps. So we're pretty much building the whole carbon-oxygen chain, then cyclizing. Whereas what we did previously was we made the macrocycle, and we had a few carbons hanging off the macrocycle, and tried to get into that end carbon to, well, selectively oxidize, which we couldn't do the Grubbs type cross metathesis, which was very challenging. Getting a high conversion was impossible. So maybe we can do things better if we do it this way. Make all of this and close. So now cleaving this back, so a vinyl addition into this thing, which would then be a carbonate. So we do this pile of Stille coupling again. This whole thing would fall apart, we lose CO2. And that would then reveal a hydroxyl here, which would close onto the carboxyl. So we practiced some of this chemistry first. So we had this, and so what we did with hydroge, which we took off the benzyl group. I think we also took off that test group, and then we could cyclize through the lactone, dival, vinyl Grignard addition, tie up to cyclic carbonate, and yes, this actually works quite nicely, and we've made perhaps an interesting analogue of the top piece of Spirastrellolide. Right, so I think one thing which I stress in doing this kind of synthesis is if you only have one student with no technicians, as maybe in the German system or postdocs, that student has to keep cooking while he's eating. So he has to continuously replenish his stocks of advanced fragments to be able to go forward and see, well, can I move on and finish the synthesis? So he had to remake this, and do now the hydroboration Suzuki coupling, and the yield is actually going up. Try double bond, do the double hydroboration. So with some optimization, we get 10 to 1 selectivity. Protect those two things as test ethers. Now we remove this test ether, without touching the other ones, radionickel off the benzyl ether to this, and you have this tetraol. And now to do in one pot kind of multiple oxidation of the top piece and the bottom piece. So this tempo oxidation works really very nicely, closes up to give the 5-membered ring lactone, takes C17 through the aldehyde. So we're sort of doing more things in one pot, so that's good. With the lithiated alkyne onto that aldehyde, didn't work well at all for chemoselectivity issues. This thing started to interfere. So I had to go from lithium to chromium, so it's NHK reaction, which works nicely then, make that bond, Linmar oxidized through to here. So now, compared to a first generation synthesis, we have a TBS ether here. This is this lactone, PMB, and so we have to just touch it with DDQ, things should cyclize up. So it does cyclize up as expected, but we got also traces of the deprotected C23 alcohol. So this time we'll have traces of that, so we stuck maybe the test group back on, or we just sort of optimized it so we didn't lose any of the test ether. So we went forward with this material, so HF to remove the TBS ether, pyridine, buffer pyridine, dival, lactone through to lactol, vinyl Grignard, 1,3-diol free alcohol, tie up the cyclic carbonate through to this. Now, C1 oxidation through the aldehyde to the acid. Pionol Stille coupling works really nicely, so many of these yields have gone up. And Phil Maltus, which is the guy who didn't want to become a management consultant, even though he wasn't tempted by the prospect of high salary and enjoyed doing organic chemistry, he could build up useful stocks of this particular advanced intermediate. So now on paper, and on this slide, of course this hydroxyl group has to be close to that carboxyl group, and it's going to close. However, in practice, it's a disaster. So when we had this system here, tried many conditions for Yamaguchi or alternatives to the Yamaguchi macrolactonization, pushed it very hard, cooked up in benzene, did everything possible, we could not get any of this out at all. If we used not the whole side chain, we got this, thinking, well, maybe it's got something to do with this, it could be a bit strange. This one did not cyclize at all. I don't have much hair left, but it's a case of, well, grey hairs, white hairs, and then no hair. I think that's the order these things go. So what on earth are we going to do to solve this problem? So let's look back at our first generation synthesis. So in our first generation synthesis, through no real intention, when we made that BC spiracetal, that test ether had dropped off with the free alcohol. This thing, actually after some optimization, cyclizes like a dream. So what we proposed was that this thing is conformationally pre-organized to cyclize, but with this thing here, that test ether is interfering with the molecule getting into productive conformation for cyclization. So it's really just sitting there and doing nothing until eventually you degrade it. So fortunately, with sort of limited time available and limited stocks, we did the obvious thing, which is now remove, first of all, this test ether. Now, first attempt, cyclize is great news. Knock off both test ethers, cyclize is even better, really good news. And if we'd had enough material, we would have knocked off all the silyl ethers, and pretty confident this would cyclize just as well also. Okay, so now all we've got to do is final deprotection, so HF pyridine removes the silyl groups. Methanolysis of this gives us now spirastrellolide methyl ester. So the good thing is that this second generation synthesis, in terms of student economy, ticks the box that it was actually done by a single, very competent, hard-working student, Phil Maltus. And the yield was now 6 times better than the first generation synthesis, but also told us that in that first generation synthesis, without realizing it, we were damn lucky. This was serendipity, and without that test ether having dropped off and saying, well, let's keep it off because it wants to be off, it would have caused probably a lot more effort to finally finish the synthesis, and who knows, maybe we wouldn't even have finished it. Okay, so second generation synthesis is really good, and one take-home message that I'm going to give you from this lecture and from yesterday's lecture. This came to me when I was on sabbatical in Melbourne, and as one does in Melbourne, particularly in summer, enjoying a nice cold beer. So this cold beer was in a bar in probably not such a great part of the city. And so I looked out the window and something screamed out at me. It was this: perseverance. So this is actually the name of a hotel in Melbourne. It looks a bit run down, and it is. But to do this kind of complex molecule synthesis, be it natural product or anything which is multi-stat and challenging, not only do you have to be very smart, experimentally able, but you've got to keep at it. You'll show not just enthusiasm, but perseverance. And with perseverance, you can achieve so much. So that's the word I'm going to leave with you. And I'm going to thank some people again. So these have all left my group. So Phil Maltus ended up going to Lundbeck in Denmark. Ed Anderson, who's just an amazing postdoc, he moved over to the dark side. So he's over in Oxford and doing very well. Steve Dalby, who's got into industry in Merck, in fact Merck in Raleigh, but now Merck in the UK. John Ho Lim, that went back to Korea, SK Energy. Olivia, who found his wife in my group. Christian, who's with Roche, and Julian with Pfizer. collaborators, well, particularly Ray Anderson, because without that authentic sample at the right time, we may not, well, it would have taken us more time to establish whether or not we actually done a synthesis. So these collaborators are actually more to do with other projects in my group, but one guy who's been extremely helpful at all times goes back to when we collaborated with Novartis on discodermaline, and Stuart Mickle has sort of given me some very useful starting materials and intermediates over the years. So this is pretty much my current group, and I probably want to thank Simon again for his contributions yesterday. Two more slides. First of all, again, commercial advertisement for Cambridge. Really very nice place, you must come and visit. So again, punting on the river. And the final slide, I really want to conclude this lecture and yesterday's lecture by saying this, of course, would not be possible without the generous endowment of Gilbert Stork. So finally, I'd like to thank Gilbert very much, and here's a very nice picture of him. Okay, so thank you very much, I'm done.
I would like to personally say that that was the clearest, most logical, and brilliant exposition of natural products, synthetic chemistry that I've ever seen. So, congratulations. Questions from the audience?
So you must have some thoughts about what exactly that particular hypothesis does in the confirmation of the
Yeah, so I can obviously show the slide. I think it will probably be a section, so I kind of just try and give it to you verbally. So with the crystal structure of that pentanol, it shows a very clear hydrogen bond network. And I think if you sort of open up a macrocycle, that kind of hydrogen bond network, if you have that free alcohol at C23, can help bring two, let's say, arms of the molecule together to cause closure. But if you have a test ether there, of course, that's not possible at all. And it may actually adopt quite a different conformation, which is unproductive for cyclization. We've done a reasonable amount of modeling of the cecoacid or something, approaching the cecoacid, trying to figure out what is the conformational possibilities of these systems with test ether or not test ether. But maybe this is the limits of modeling. We never got a clear result from the modeling, so it's more a case of thinking about hydrogen bonding and how that could be productive. Now, of course, in terms of biosynthesis, most likely what happens is the carbon-oxygen skeleton spot built up, spiracetals are built up, tetrahydropyrite rings built up. There's no protecting groups. That thing is conformationally organized so that for the sort of phytoesterase cyclization step, I know it's got an enzyme to hold it, we probably don't even need it. It sort of cyclizes with no difficulty.
Ian, I had a question. It's kind of a philosophical question that has to do with a signature of your work with aldol chemistry, is that you have, rather than use chiral auxiliaries, which have been widely utilized for stereoselective aldols, you build your chiral auxiliary essentially as part of the molecule. Can you comment on that and how you came to that?
I think I was influenced by Gilbert, this sort of typical Stork approach. You start with one stereocenter and relay that stereochemical information to as many other as possible. The kind of history of this is kind of interesting. So, first time I came across Rochester was when I was with Gilbert, but it didn't actually feature in the project I was working in. I think we probably tried to use it for something, but maybe it was to make a model to do some chemistry. And then, of course, the source of it was Clark Still, because Clark had used it in his Monensin synthesis, and he'd managed to get it from Roche. And so when I went back to Cambridge, I thought, it's potentially a very valuable starting material. And at that time, people, of course, had made the aldehyde and tried to do chemistry with the aldehyde, but the level of stereoinduction with that alpha chiroaldehyde is not that great. So I guess our analysis was, well, why don't we look at the ketones and try and do aldol reactions with that and see if we can use that stereocenter, which essentially you buy, to control now 2 stereocenters. And just progressively we found, yes, we could do that, we could set those stereocenters. We'd get almost any permutation. We could do it with ethyl ketone, methyl ketone, alkoxy methyl ketone. So just very general and powerful. And as we used more and more elaborate aldehydes as the components, particularly if those aldehydes had some stereocenters in it already and maybe even got a bit crowded, the chemistry worked well. And then the next stage was, of course, well, we did play around with reagent control and IPC boron chloride. That's actually very useful, particularly if there's no high level of substrate-based stereoinduction, so use the chiral ligand. And in situations where you need to overturn substrate selectivity, very, very powerful and used in the Novartis synthesis of discodermalide as one of the late steps. And then the next evolution of it was to go from Roche ester to lactate, and then that allowed us to do, well, maybe the equivalent of an Evans syn-aldol, but for an anti-aldol. But we had this appendage, and as you say, that appendage is not really just a chiral auxiliary. We don't lop it off. We use that chiral auxiliary to sort of build up more of the skeleton. So, it's, I have to say it's a classical Gilbert Stork approach, and that's his inspiration to me, or at least one of those inspirations.
Great, thank you. Other questions? If not, I'm going to lure Ian back here behind the podium to shake his hand in front of the Gilbert Stork Award. Thank you very much. It was fantastic.
Okay, so
and there's a reception. There is a reception in the Shane Atrium starting now.